Yeah, I think let's get started. So it's 9:15 now. Okay, good morning, everyone. So it's my pleasure to introduce Dr. Matthew Witman. So Dr. Witman graduated from UC Berkeley in 2019. And then after graduation, so he started as a postdoc at Sandia National Lab, and then he was promoted to senior staff member. So he's currently using his expertise on data-driven material discovery to help lead two important DOE initiatives. One is called HyMARC, another is called HydroGEN. So those two initiatives are focusing on hydrogen storage and hydrogen generation. So without further ado, please join me welcome Dr. Matt Witman. The floor is yours.
All right. Thanks, Hao-Lang. Thank you for having me today. Thank you, everyone, for coming. Today, I'm happy to present some of our research at Sandia on accelerating the data-driven discovery of materials for hydrogen storage and generation. And I'm at the Sandia National Labs, Livermore, California site. Sorry, my slide's not advancing here. So before I begin, I'd like to thank a bunch of people who have contributed to the work you'll see today. A lot of this work is, multidisciplinary with people of different expertise and experiments, ML, first principles, and this is spanning. Sorry, if you could mute your mics, please. I'm hearing someone. This.
Hi, Dr. John. I think the speaker's mic is muted.
There we go. Thanks. I should be unmuted now. So as I was just saying, I'd like to thank everyone who contributed to this work and that it's been supported by HyMARC, HydroGEN, and internal Sandia funding. Sorry, my slide's long advanced when the laser pointer is active. There we go. Okay, so as we all know, there's never been a greater necessity for new and improved materials that can improve our energy security and help mitigate greenhouse gas emissions. It's become very clear that human-caused climate change from fossil fuel emissions are causing drastic increases in global temperatures. We've seen that in the past few days here in California with 30 degrees Fahrenheit above the average at our site. So we need to do something about this urgently. So that means that there's a massive need for decarbonized domestic energy. This infographic's slightly old, but the breakdown of energy, the distribution of energy requirements in the US is about the same today. So we have these various sectors in which we consume energy, and things that I'm highlighting here in transportation and industry are, there's a lot of different applications like heavy duty vehicles, airplanes, maritime shipping. On the industry side, there's all sorts of high temperature applications, chemical synthesis, steel production, things that emit massive amounts of CO2 and are going to be very, very difficult or even unlikely to be decarbonized with a renewable source of energy plus batteries. So that's kind of one of the reasons why the DOE established this first energy Earthshot focused on hydrogen. And so, the question is, why isn't green hydrogen mainstream yet? And it's because there's whole sorts of challenges associated with hydrogen. The biggest, of course, being that the storage and the generation of carbon-free hydrogen are not sufficiently cost competitive with other technologies yet. So we need to develop new and improved materials. They're going to make it an economically convincing case for rapid and widespread adoption of hydrogen. And again, that's where this kind of first energy Earthshot came in from Secretary Granholm. So there's been some really interesting recent commitments to hydrogen, both at commercial scales and from industry. So I'm just highlighting a few of these here in case maybe you haven't heard of some of them. There's an Australian startup that's providing these home energy storage solutions that are based on metal hydrides. You can buy light duty hydrogen powered vehicles like the Toyota Mirai. That car's actually been out for a few years now. Airbus has interestingly made some pretty big commitments to trying to achieve hydrogen powered aircraft over the next 20 years. An interesting development from Alstom, which is a car, well, it's a pretty big conglomerate in France, but they've recently released this hydrogen powered light rail train that's just been deployed at a bunch of places in Germany recently. And then you have even some of these, traditional fossil fuel companies that are making large commitments to utility scale generation of hydrogen. So Shell is committed to a huge offshore wind plant in the Netherlands to produce green hydrogen. So the question is, why are we going to be researching materials-based solutions in hydrogen science? Well, we have various needs, a current solution, and then there's a significant advantage to a materials-based solution that, if we can design these optimal materials, could actually improve upon what we do right now. So in terms of the generation side, most hydrogen today is generated by steam methane reforming or something that releases CO2. So it's kind of defeating the purpose of this green energy transition. So of course, we want to be researching materials that can exploit renewable heat, electricity, or light to split water and generate green hydrogen. And then most of the applications you're seeing here are going to rely on today compression of hydrogen to 700 bar for storage. But in order to compress hydrogen to 700 bar, we have expensive and energy intensive mechanical compressors. And one alternative with materials-based is to use thermal compression that has no moving parts. Could potentially be much cheaper to do this compression. And then finally, once we compress the hydrogen, we need to store it somewhere. Right now, especially in something like the Toyota Mirai, that's done with these pretty expensive tanks. You have to get the hydrogen up to 700 bar, but if we can come up with materials-based solutions, we can achieve hopefully the same volumetric density at much lower pressures and significantly reduce the cost of that storage. So that's just a high-level picture of what we're looking for in this field. So just to touch on, a little bit more of the material science. So we're going to be looking at metal hydrides for hydrogen storage, which is, you have a metal or high entropy alloy that, can absorb hydrogen in this reaction. And how we measure that experimentally in the lab is we do these PCT curves. So we apply pressure, measure the hydrogen uptake, and here you see this, phase transition that occurs in the material that allows you to store a large amount of hydrogen over a low pressure swing. So once you've gone in the lab and measured these PCT curves, you can get the delta H, delta S, and capacity for these reactions. But it takes a really long time to make and test these materials. And from a first principle standpoint, it's really, really hard, if not impossible, to do this exact PCT curve prediction from first principles, especially when you even consider looking at more than a few materials or doing this in high throughput. So the best we can kind of do is a low sample estimation of delta H. On the hydrogen generation side, an example of that we're going to focus a lot on in this talk is solar thermochemical water splitting. So this is where you take a metal oxide and you thermally reduce it to liberate oxygen from your metal lattice and create vacancies. And then you re-expose that metal oxide to steam to reoxidize the material and generate hydrogen. So this is the particular material that Sandia studied a lot, BCM12. And here you can see the experiments that show these nice thermochemical redox cycles where you're generating hydrogen and oxygen by alternating between this reduction and oxidation temperatures. So again, experimentally, we can directly measure the material, the most important material properties, which are, of course, this performance here. But again, it takes a long time to do these experiments. And from a first principle standpoint, we certainly can't, simulate these cycles from first principles, or at least it's very difficult. And instead, what we typically rely on is computing or estimating the vacancy formation enthalpies. And again, that's not really possible to do in super high throughput at the moment. So we've run into these barriers where we want to test or have these optimal materials, but it takes too long to make them and test them. And if we want to go to a first principles approach like DFT to try and predict some of these properties, it takes us a very long time to compute a proxy of their performance, even just for a small number of materials. So this slide might be a little bit redundant for this audience, but just to show where we're coming from, typically the traditional paradigm for materials discovery has been, we have some chemical intuition about the problem. We go make the material, we characterize it, and we test its performance. Depending, of course, on what application it is, these experiments could be fast, but they could take an extremely long time. So, with the advent of high performance computing, then we could turn to physics-based simulations to try and help accelerate this process. So we develop some kind of first principles theory and then run the simulation and predict performance Again, depending on what you're dealing with, that could be really fast, or it could also be intractable. But if we can collect enough data from either experiments or physics-based simulation, we can feed these machine learning pipelines, which have become increasingly popular in material science in the past few decades. And once we have a good way of featurizing our materials and constructing and training models, the point is that running these machine learning models to predict performance is a trivial task compared to the actually making these experiments or running these physics-based simulations. So in hydrogen science, we're really looking for new predictive capabilities that can evaluate the critical materials performances that are needed to evaluate its ability in a particular application, and that they need to be efficient enough to accurately predict the properties of thousands of candidate materials that we're interested in evaluating. So some of the work that we've done at Sandia has focused on some of these material classes you see here, and we've been showing that you can accelerate this discovery of materials by many orders of magnitude through these data-driven techniques. I'm not going to talk about metal organic frameworks in this talk today, but I'm going to be talking about high-entropy alloys, liquid metals, and metal oxides for hydrogen storage or hydrogen generation. And the common theme is that there's hundreds of thousands or thousands of potential candidates that we can conceivably consider for these applications, and then we identify orders of magnitude less materials that are considered the most promising, and then we go into lab and test them. So my goal is to give a brief outline of the materials discovery tasks that we've been performing in the past 3 years. So I'm going to try and cover each of these in about 10 minutes. In the first part, we'll be talking about hydrogen generation and accelerated screening of metal oxides for thermochemical hydrogen production. And then by implicitly, that means we can actually discover oxides for more applications. But that's going to focus on the use of graph neural networks to directly predict vacancy properties and use that to do high throughput screening to identify optimal materials. In the second part, we'll be focusing on liquid metals for a new hybrid thermoelectrochemical water splitting scheme. And there we'll be using compositional machine learning models to directly predict melting or phase diagram properties, and then using that again, of course, for high throughput screening and down selection of top candidates. Then we'll shift gears into the storage side, where we'll be talking about how you can identify Pareto optimal high entropy alloys for hydrogen storage. Again, we'll be kind of focusing on these simpler compositional machine learning models, but doing direct hydride thermodynamic predictions. And then in the last part, I'll kind of address some of the shortcomings of part 3 and say how we're moving towards directly optimizing the thermodynamics of these high entropy alloys and hydrides through a combination of machine learning and first principles. And again, we're going to go back up in complexity towards these graph neural networks to show that you can screen the energy landscapes of these materials in high throughput and use that to help construct elements of the metal hydrogen phase diagram. So we can jump into part 1. And again, this is a collaboration with a group of people here at the National Labs and at Brown. And so we're going to be talking about how we can use graph neural networks to directly predict relaxed vacancy properties, and how we can use that to high throughput screen new materials in thermochemical water splitting. But that also means we can discover new materials for solid oxide fuel cells, CO2 conversion, and thermochemical energy storage. So I already kind of introduced this topic, but let's briefly refresh. So this is actually the solar tower at Sandia, New Mexico. So that's one of the reasons why Sandia has a pretty large program in this solar thermochemical water splitting program, or STITCH. And it's a prominent pathway for green hydrogen production, or the production of hydrogen without CO2. So I already went over the mechanism. We have a metal oxide that we thermally reduce to liberate oxygen. We re-expose the steam at a lower temperature, and then that generates hydrogen, and we keep going with this thermal redox cycle. So there's many different variants of different ways you can play around with these cycles with more than 2 steps and all these other things. So if you go on the DOE website, there's more than 300 proposed types of cycles. We're focused on this most simple 2-step cycle, and the reason why we're doing this research is that there hasn't been a metal oxide discovered yet that meets all these requirements that would be needed for it to be commercially viable, such as a sufficiently low thermal reduction temperature, stable enough, fast enough kinetics, et cetera. But the top materials that we've studied in the lab at Sandia is this BCM12R material. But if we want to create a new oxide and test it, it takes a long time. So what we do with to evaluate new materials is typically use something like density functional theory. And if we compute the oxygen vacancy formation enthalpy of all sites in the crystal structure, we can kind of narrow down whether a candidate should be possible to be used in stitch based on these kind of criteria here, which is basically just saying that all these oxygen vacancy enthalpies should show up in this sweet spot range, and at least one of them should be, and that all of them should be greater than the minimum. But there's different ways you can play around with it, but that's the kind of the first level down selection criteria that it has to meet. So you can do this for a handful of materials, but it still takes a long time if you're going to do this with DFT. And the reason is because we need to have a host structure that we relax with DFT, and then we have to compute that vacancy formation enthalpy for all the symmetry sites in the crystal. So if there's n symmetry sites, we have n+1 DFT relaxations we need to perform, but we can do that and compute this delta H of vacancy formation enthalpy. So my collaborators at NREL have a nice first principles DFT workflow to do this, but it's still costly. So we built up a pretty diverse database of different crystal structures, different compositions, and done these detailed host and vacancy relaxations. And in about a year's time, we came up with about 200 host structures and about 1,500 relaxed defect enthalpy predictions. But in this kind of search space, if you go into materials project, you can find tens of thousands of host structures, containing millions of symmetrically unique defects. So you would never be able to, kind of just chug through this with brute force with DFT. So the goal is to drastically accelerate this process. And so our goal is to come up with a very generalizable approach to modeling these vacancy defects to enable this new materials discovery exercise. So some things that won't work, for example, are a compositional featured machine learning model, because you won't be able to differentiate the different symmetry sites. So if you have something like manganese oxide, you have different symmetry sites for these different oxygen atoms, in which the relaxed vacancy formation enthalpies can differ by 0.6 eV. Now, if you try and derive your material features for a model purely based on the composition, the corresponding feature vector will look the same, whether it's the first or the fourth oxygen defect you're looking at. So your inputs would be identical, but the local structures are different. So that's a problem, right? If your target value is differing by 0.6 eV. So there's been some really cool, interesting recent work to model these defects with much higher efficiency than DFT. So this recent paper derived this very interesting linear model based on these hand-engineered features that account for some of the structural information, so that they were able to predict oxygen vacancies with a pretty good mean absolute error, and it's validated in these ABO3 perovskites. But this kind of hand-derived linear model won't work for the cations in this crystal structure, and you would probably need to rederive this expression if you move to a different structure class, for example. Kind of a similar thing was using random forests to predict vacancies in 2D materials. But again, there's similar potential limitations where it's validated for these 2D material classes, and you would need to rederive your model as soon as you went to a different structural class. So one thing that's really attractive is the automated feature extraction capabilities of graph neural networks. And you can use this to efficiently and use this for efficient and generalized modeling of vacancy formation enthalpy. So to quickly go over what GNNs are, the power of GNNs is that you basically take a crystal structure and you can interpret the nodes as atoms and the bonds as edges. And then once you basically concatenate the information between neighboring nodes and edges and pass them through a feed-forward neural network layer, you basically provide an update after each convolution to the feature vector that's on each node. Once you pool that information all together in some kind of pooling operation, like a sum or an average, you end up with this feature vector X crystal that is representative of your material. And then once you apply any final feed-forward layers, you can predict some kind of target property of interest. So we modified this to be more specific for predicting vacancy formation enthalpies. And so again, I just want to remind you that, when you're doing this with DFT, you have to do N relaxations for every single symmetry site in the crystal. And that's because you have to remove the atom, perform the defect relaxation, so, measure the energy difference, and that's your relaxed defect formation enthalpy. So what we're proposing with the machine learning model is, can you actually predict that relaxed defect formation enthalpy just knowing the host crystal structure, and then just telling the model which index would be the node that should be defected for the property prediction. So in this very simple example graph, you have nodes with their feature vectors, and then just an edge between those two nodes. And at the beginning, you encode your feature vectors by just looking at, so node 1 is oxygen, so we include things like the covalent radius, electronegativity, et cetera, of oxygen. And then in this work, because we actually know the host crystal structure and we have that calculation, you can add in other things like site-specific features like the oxidation state. And that's relevant, of course, for cations, which can adopt multiple oxidation states. Then you perform these convolutions. It's a pretty involved expression here. We don't need to go over all of it, but it's just basically just the concatenation of nodes and neighboring nodes and their edges, and then passing those feature vectors through feed-forward neural network layers. And then some final activation function that gives you the new feature vector at the teeth convolution. So then the thing that you need to do in order to predict defect formation enthalpies is, instead of doing a global pooling, you just do a node level prediction in your graph. So you basically just take out the node that should be defected at the end of the convolutions. We actually threw in, concatenated that with some of the other global host properties like band gap, effective electron mass, and things like that. And then you pass that quantity through any final feed forward neural network layers, and that gives you this relaxed defect formation enthalpy. So all you need is the host input geometry. You tell it which node is going to be defected, and you get out the relaxed defect formation enthalpy. So we validated this approach. Our data set, as I mentioned, is up to about 1,500 unique symmetry sites across 200 crystal structures. So that's a pretty small data set for deep learning. So here we're just showing the decrease in error as a function of the buildup of the training set. So we're still in this data limited regime where the model accuracy is going to still improve quite significantly as we add more data. And so that's, of course, what we're working on in future steps. But here you can see that the oxygen mean absolute error is below this 0.5 EV, which is kind of like our target for being able to do successful materials discovery. And here I'm showing the parity plot for all the test set predictions across all the K-folds in our cross validation. And you can see, so this is the exact same model that's predicting, oxygen and cation vacancies, same exact model, same exact weights. So that's what we mean by this approach is generalizable, and it's really only going to be limited by the amount of data that you give it. So again, we can get to a sufficient oxygen error that we can do this for materials discovery, and this is super fast to train and execute. And then we can predict, any crystal, the vacancy of any crystal site in the structure. So some things I won't talk about today, but you could take a look at in the preprint are the effects of different encoding strategies. What happens if you try and predict a compound that has a cation that wasn't in the training set, and things like that. But just to convince ourselves that this model is like high performing and not overfitting, is we can apply the model to two different crystal representations, one from the materials project and one from NREL MatDB, which is where the training data was derived. And for all these structures that only have one symmetrically unique oxygen site, we can plot the difference between those two predictions, and that difference is below the mean absolute error. So the model is robust to any kind of small variations in crystal structure or DFT settings. So we went ahead and used this to screen the materials project. So we then went ahead and high throughput screened a bunch of metal oxides to rediscover, which actually rediscovered some known water splitting oxides, and of course identified new ones that we're going to now test in lab. So again, I mentioned we're looking for this requirement that all the defects are above some minimum threshold, and then at least one is in this critical range, but in reality, you'd probably want all of them to be in this critical range. And then the final key down selection criteria is that we have actually a target chemical potential range of oxygen that's defined by the Stitch process. So our material, of course, has to be stable within that chemical potential range. So we have this additional stability criteria that says, the material must be stable. The material's grand energy above the whole must be below some threshold and intersect with the target chemical potential range. So we can do this down selection and quickly screen all of these materials. And this is an example of one material where the range of vacancy formation enthalpies of oxygen is huge, and it's something that we need to discard because the lowest one is actually kind of below this critical threshold. So we can apply various, iterations or permutations of these down selection criteria to make the selection more stringent or less stringent. But if you make the most stringent criteria, you kind of get down to the order of 10 new materials that we'd want to test in the lab. And what's cool is that a lot of these materials aren't in the kind of common AbO3 perovskites, Ruddleson Popper phases, mixed metal ferrites, et cetera, that people have traditionally studied for stitch. And it rediscovers some of the known materials like BCM12, which is kind of promising for the prospect of some of these new predicted materials. And then just a quick comment about this. So we have this database of oxygen vacancy formation enthalpies, but because people in the literature have also proposed ideal target ranges for solid oxide fuel cell cathodes or CO2 conversion via reverse water gas shifts, we can quickly go through these materials and pick out ones that might be useful in these other applications. Here I'm showing the minimum of that, the minimum stability for the material at the oxygen chemical potential versus the range of its defects. So again, you kind of see this classic defect trade-off where the higher and higher, or the lower and lower the defect formation enthalpy gets, the less and less stable your material is at higher reducing conditions. So that's kind of the trade-off that we're going to constantly be operating in all these applications. So we kind of want to pick out materials that are on the lower bound of this Pareto front. So again, when we do this, we actually find materials that people have considered experimentally for these different applications, and we can suggest new ones. So all of this is open source, the data, the repository to reproduce the results, and the code to do the defect predictions. So in conclusion, we can screen these new metal oxides many orders of magnitude faster than it would take to do everything with DFT, and quickly target new materials for experiments, which we're working on. And there's a lot of room for future development to expand the cation space, go beyond oxygen, look at nitrides, fluorides, and any other kind of materials, and add more structural diversity like 2D materials. Okay, so now I'd like to switch gears into, again, sticking with generation, but using a different type of material, liquid metals, and a novel hybrid thermoelectrochemical water splitting scheme. So the key concepts for this part will be, we're using compositional machine learning models for predicting melting and phase diagram properties. And this is going to allow us to do rapid down selection of high priority candidates for experimental testing. So my colleagues had proposed this kind of hybrid thermoelectrochemical concept for renewable hydrogen production based on liquid metals. And the motivation is that, current concentrating solar power, cannot reach the temperatures that we need for the previous application we just showed, at least not at a commercial scale. So we're kind of looking for things that can split water below 850 Kelvin if it's coming from concentrating solar, or even below 550 Kelvin, which is kind of the waste heat from a nuclear reactor. So the way you would do this is with a liquid metal solution where you sparge in steam, and then you oxidize a liquid metal melt to produce hydrogen. And then in order to regenerate the liquid melt, you would do this electrochemical reduction of your oxidized liquid metal to liberate oxygen and refresh the liquid metal melt. And the goal would be to hopefully do this at a potential less than is required for typical electrolysis today. And so this is kind of the thing that Boston Metal is working on, for direct iron reduction, same technology, but this would just be applied to the liquid metals that we're studying in this problem. So the goals are to drastically reduce the operating temperature compared to stitch, which we just talked about, and then regenerate the liquid metal with the electrochemical reduction scheme. And so here I'm showing the water splitting reaction, and the goal is actually to, as I mentioned here, so actually let me step back for a second. So what are some of the desirable attributes for what should be what this binary liquid metal should be? Well, of course, we need to have a low melting temperature across the binary composition space. We actually want just that one metal is preferentially oxidized while the other remains a liquid carrier. So, in other words, the system isn't going to just freeze as soon as you start oxidizing the metals. And we want to balance the spontaneity of the thermochemical oxidation versus the potential required for the electrochemical reduction. So here's the, kind of the proposed scheme. We have two different metal elements in our melts, and hopefully we preferentially oxidize one of them while the other inform these kind of small, well-distributed metal oxide particles in the melts, while the inert metal remains liquidous, as a carrier, and so the system doesn't freeze and we generate hydrogen. So here we've just used a few relatively simple data-driven models to kind of go from the space of, well, there's maybe 70 conceivable elements that you could possibly even think of using. If we're limiting ourselves to binaries only, equimolar binaries, then you have 2,415 possibilities. And how do we get that down to just a handful that we can actually test in the lab? So first we did a kind of a simple machine learning modeling of liquidus curves. So the reason why we had to turn to machine learning is we wanted to just go into FactSage or some commercial thermochemical database and get all the melting temperature, all the liquidus curves for all binaries. But there was only data for about a third of them, reference data for about a third of them. So we can just develop a quick and simple machine learning model to predict the melting temperature of a given composition, right? So in this case, you're just looking at a generic model like gradient boosting tree regression, and you can use things like MAGPIE features to derive this compositional machine learning model. This just involves things like covalent radii, electronegativity, volumes per atoms of the elemental solids, weighted by their atomic fractions, and then combined in kind of simple mathematical operations. So what's kind of was potentially surprising is that such a simple featurization strategy allows you to qualitatively and semi-quantitatively get the liquidus curves for holdout set binaries. So these are materials completely outside the test validation the train validation and test splits. These are ones that weren't in FactSage at all, but we were able to get the ASM phase diagram, for example, test the machine learning model and its predictions. And so for these binaries, you can clearly see that the model can capture these eutectic and congruent melting behaviors and the mean relative errors across this entire composition space of the liquidus curve is actually not too bad. So that enables us to just make sure that we weren't missing any materials in this initial from this initial FactSage data set. So kind of the more important part then is how can we determine which ones are have the right thermodynamics for this proposed water splitting reaction. So after we narrowed it down to about 100 materials with the right with the desired melting range, we wanted to create what are called these OH predominance diagrams. So in order to do that, you need to know the Gibbs free energy of the different phases in the system. And there was this interesting recent paper where Bartel et al. Used this CISO model to derive a descriptor that you can use to correct DFT calculations to get the Gibbs free energy of that phase at a given temperature. So you perform a DFT calculation, you use this kind of remarkably simple correction factor for a given compound, which just relies for solids the volume of the DFT relaxed cell at a given temperature, and that gives you this correction that when normalized for the elemental Gibbs free energies, you get the Gibbs free energy of formation of that compound. So if you can measure that, then you can compute the grand potential. So in the system, we're open to oxygen and hydrogen atoms, but I've rearranged that expression based on the chemical equilibrium expression for water to re-express this in terms of control variables that we actually control in the lab, which are chemical potential of hydrogen gas and chemical potential of the water gas. And once we do that, we can construct these OH predominance diagrams in high throughput. So construct the phases that minimize this grand potential. And you can see here, we are plotting the stable phases as a function of now things we control in lab, the hydrogen chemical potential and the water chemical potential. And if you assume they're ideal gases, you can map that to the partial pressures you see here. But what we're looking at are, so down here in the bottom right corner is the fully reduced system. So that's our neat liquid metal melt. And as I mentioned, we're looking for preferential oxidation of just one of the metals. So we have these two descriptors, the chemical potential at which the first metal oxidizes, in the zinc bismuth case, that's zinc, and then the chemical potential at which the second metal would oxidize. So what we really want are materials that exhibit a range of these, the preferential oxidation of the first metal, and we want large values, or at least non-zero values of this delta, because we want to only be able to oxidize only one of them. So that's what these two descriptors are accounting for. So we can do that in high throughput for all of these remaining, well, we could do that for all the binaries. It's simple to compute, but we compute that for the 100 remaining candidates. And here I'm showing, so again, this is the chemical potential at which the first metal oxidizes and the delta at which the second metal oxidizes. And then kind of the color, or sorry, the bullet size here accounts for what % of the liquidus curve is below that target temperature. So you can very quickly pick out just a few binary systems that would be the most experimentally promising to look at, because, you know, again, they melt below the target temperature, and they have a range of chemical potentials over which the first metal oxidizes, and non-zero values of this delta at which the second metal oxidizes. And furthermore, these are all kind of accessible and cost-effective raw materials. So my collaborator, Tony McDaniel, is the experimental expert on all this stuff. So he actually went into lab and, you know, started off with this off-equimolar zinc tin alloy, and was able to achieve significant hydrogen conversion in this flow reactor, where he sparges in steam at different input hydrogen or water to hydrogen ratios. That's the different steps you see here in this blue curve. So he's feeding in gas at the same pressure, but kind of changing the steam to hydrogen ratio. And you can see actually that the hydrogen production above the baseline here, that's this area with, you know, under the red integral under this red area, is kind of constant as a function of the steam to hydrogen ratio. But over the course of this experiment, he was able to convert 11% of the zinc to zinc oxide. So there's definitely still some optimization needed, but there's promising signs that you can design these flow reactors to convert steam into hydrogen. So going into SEM and EDS characterization, so it's very hard to do any kind of in situ experiment to characterize this in this, you know, high temperature reactor, but we can freeze the reactor shot afterwards and then go in and look at SEM and EDS. And here's maybe perhaps luckily we captured what looks like 2 bubbles in the frozen into the reactor shot. And you can see these dark flakes. Actually, when you look at the EDS, these dark flakes around the bubble or little particles correspond exactly to zinc oxide, which are, you know, the red and the blue embedded in this tin matrix. So it confirms that, you know, we're forming zinc oxide and not tin oxide in this system. So one thing that we're now moving towards is getting some atomistic insights into this process. So we've you know, done some ab initio MD simulations where you can kind of create these cells and artificially change the volume to induce bubble formation in the melt. And then you can apply metadynamics to kind of look at you know, free energy barriers of various processes. In this case, we're just looking most simply at, you know, the association and dissociation of hydrogen in the melt. So you can, you know, run these AMD simulations, analyze the trajectories, and here in blue you're seeing the distance between the hydrogen atoms, which is being biased by the metadynamics, and the distance of hydrogen to the closest metal atoms. And you can see that a hydrogen formation is really only occurring and persisting when those hydrogen atoms can recombine on the surface of this, you know, induced bubble and, you know, kind of diffuse around in that void space. So if you look at the free energy profiles as a function of the density, you can see that, you know, you need to actually increase, you know, you need to actually have this bubble form for the free energy of that process to be downhill. So these are all just preliminary results, but just wanted to comment on, you know, what direction we're going with this now. So in conclusion, you know, we've taken thousands of possible binaries, and, you know, if you apply this machine learning and data-driven discovery workflow, it takes just a few minutes to identify top candidates, and we've, you know, experimentally validated some of them in lab. And there's a lot of room for future development from atomistic and mechanistic insights from machine learning plus molecular dynamics, and, you know, going beyond these simple binary systems. So in part 3, we'll talk about high entropy alloys for hydrogen storage. And some of the key aspects will again be these compositional machine learning models to predict hydride properties, and the fact that we can use this to directly predict and high throughput screen new materials and find ones that are destabilized, which I'll talk about what that means in a minute. And then we can actually target multi-dimensional Pareto optimal materials to actually go in the lab and make. So the first thing that we want to emphasize is that, you know, we can actually use these explainable machine learning models to directly predict these metal hydride thermodynamic properties. So again, we have this metal hydride. I explained how we collect the PCT curves, and from those PCT curves, we can extract the enthalpy and entropy of formation, which basically allows us to predict what the equilibrium plateau pressure will be. And that's kind of the main thermodynamic property of interest for pretty much any application. Tells you, what pressure you release hydrogen from your material at a given temperature. So all this data has been manually accumulated from the experimental literature in this nice HyMARC database that Sandia was kind of in charge of for a while, but this was all done pre-machine learning days. So it takes actually a ton of effort to clean and remove errors, and really only a small fraction of the database is actually usable at the moment for training a machine learning model. But we can actually go ahead and featureize these materials again using compositional features. We do this because there's a lot of substituted materials in the database for which we don't explicitly know what the crystal structure would be, so it'd be very hard to imagine using things like graph neural networks for this. Here I'm highlighting one specific feature again. This is the composition weighted mean of the ground state volume per atom. So just one example of a feature that comes out of MagPi. And so actually when we try and train to predict this log equilibrium plateau pressure, we actually have a pretty reasonable model that is successful only again using these compositional features. So it's interesting to dive into the explainability of things like gradient boosting trees with things like SHAP analysis. I don't have too much time to get into the details, but basically what this SHAP analysis does is it breaks down how a specific feature value impacts the model's prediction deviating from the baseline or the average across the data set. So when you look at this plot, you can clearly see that the model is using this new PA value as the most important feature, where a low value of new PA tends to create a higher plateau pressure, and a high value of new PA tends to decrease the plateau pressure. So, you could actually just fit a linear model with new PA, and the accuracy isn't bad. It's still, 60% higher than this, but it's still, this log plateau pressure is quite closely correlated with new PA, and that's kind of our first order design principle. Okay, so we can use these models to predict destabilized high-entropy alloys. So as a quick refresher, high-entropy alloys are these multi-element systems that are approximately or close to equimolar on some defined lattice type. And again, they're solid solutions, so that kind of forces us to use these compositional machine learning models as the first approach here. And so we're going to target all the possible equimolar 4, 5, and 6 component systems in this elemental space. And that automatically gives us hundreds of compositions. So we're going to need a modeling approach to predict them. So we're not just going to assume that all of these high-entropy alloys could actually be made. We can actually get this phase stability down selection step, where we look at this tabulated experimental data from the Senkov review, where he's gone through hundreds of examples in the literature and classified whether a given composition can form a solid solution, whether it decomposes into intermetallic phases or is some impure mixture of the two. And so if, again, you just use a simple gradient boosting classifier model, you can get around 75% class weighted accuracy on this prediction task. And so, we're only going to consider materials where, this model predicts that a solid solution can indeed be informed. Interestingly, if you do the interpretability analysis, this model is basically just the Hume-Rothery rules with a few other features thrown in. So we can go ahead and screen our entire space. We choose, again, materials that are predicted to form this solid solution. And then here's the prediction of the equilibrium plateau pressures for all materials. In blue is the original high-entropy alloy hydride discovered, which is actually one of the most stable in the data set. And so you can see how many orders of magnitude this data set is predicted to span in terms of this thermodynamic stability. And so we chose 2 aluminum containing compounds that kind of span the entire length of the entire distribution of the predicted pressures. And so we went in lab and made them with our collaborators. You can see here's some nice EDS images of before and after hydriding for these samples. You don't see any elemental segregation. They remain high-entropy alloys as you cycle them. And then if we go and do the PCT curves, again, blue is the original material, and in squares are these new material aluminum containing compounds that we predicted, and you see several orders of magnitude increase in the plateau pressure. So if we plot, experiments versus machine learning predictions, again, pretty good correlation between those two. And then also, if you look at the experimental or the experimental or predictive log equilibrium plateau pressures versus, again, this primary design descriptor, again, we get a nice linear correlation. So it's, validating the machine learning model and also this first order design rule. So finally, I'm going to speed things up since I only have about 10 minutes and we don't have time for questions. We can, jump into different models, right? So we don't need to just look at equilibrium plateau pressure. Some of the data in this HyMARC database is actually the estimated saturation capacity. So how much hydrogen these materials can uptake at its maximum. But we also have the individual thermodynamic properties. So some few things I want to highlight is that we've included, domain specific features that have improved these models. So things like the composition weighted mean of the binary hydride formation enthalpies improves your property prediction significantly. But you can also see that these properties are codependent on a lot of these properties. So, the similarities that you see and the feature dependence basically mean that so as H to M goes up, so does delta H. But in general, we want those things to be oppositely correlated for optimal materials. We want a low delta H, but a high hydrogen to metal ratio. And then the other caveat that I want to share with these models is that the HyMARC database has a huge skew in its underlying data distribution. Most materials are peaked around, around these central values. So as soon as you try and start predicting materials on the very edges of the distribution, your error starts to explode. So that's one limitation of the model. But nonetheless, we've, in this kind of last stage of the project, we've mined as many experimental values of high entropy alloy hydrides as we can from the literature and added that to our training data. We've gone to a larger screening space where we now have an even expanded set of elements including magnesium, which is kind of an interesting challenge because there's no magnesium containing hydrides in this training data. And finally, we're going to just briefly mention that using these enthalpy predictions and these capacity predictions, we can define the set of Pareto optimal materials. So a Pareto optimal set of anything is, happens when you have these competing objectives that you want to maximize. So in this case, we're looking for optimal thermodynamics. We want a delta H around some target value. We want the highest possible volumetric and gravimetric capacities and, the lowest raw material cost. So this is a multi-dimensional Pareto front, which I've projected just, down into 2 dimensions in terms of the delta H and the capacity. But we can rapidly pick out, there's only 100 materials in this blue line. Again, this is the 4D front projected into 2D, but we can rapidly pick out those materials we want to test in lab. And that's what we're going about doing right now. All right, so in the last few minutes, I'm going to quickly go through this project where we're trying to optimize the thermodynamics of these high entropy alloys and hydrides using a combination of machine learning and first principles. And we're doing that because we're trying to address some of the shortcomings that exist in part 3. So the key concepts will be using graph neural networks on ideal lattices to high throughput screen random alloys and use that high throughput screening to directly predict thermodynamic properties from first principles and use that to extract information about the metal hydride phase diagrams explicitly. So some of the limitations of the previous section were that these compositional models are hampered by limited experimental data. Reasonable accuracy is unlikely when you have materials that are significantly out of the training distribution. And we only have the certain values in HyMARC database that don't contain key information that we might want from the phase diagram. Like instead of the saturation capacity, we probably want the reversible capacity. We want to know if, what happens if there's multiple phase changes, et cetera. So before we would just suggest a new composition, and based on our limited and unbalanced experimental training set, we would train a model that could, we would filter things based on these simple phase classifier and, try and directly predict these properties. But our new ultimate goal is to suggest a new composition and actually do DFT screening of random alloy configurations and random hydride configurations in these exemplar lattices and use graph neural network models to predict the formation enthalpies and high throughput from an idealized structure representation, which I'll mention in a minute. And if we can do that in high throughput, then we can feed first principles thermodynamics calculations or simulations to kind of more rigorously predict the alloy stability itself And then finally, directly predict the pressure, composition, temperature curves and subsequent thermodynamic properties. So going back to GNNs now, these are kind of an ideal situation for doing this configurational energy screening in high throughput. So typically we take a DFT structure and we optimize an initial guess of the structure, let's say it's XFCC, to get the relaxed crystal structure XDFT and its formation enthalpy. And of course, you could create a model to predict the formation enthalpy using the DFT relaxed representation, but that's not useful for high throughput screening because you need to do the DFT relaxation to get the model inputs. So just like in methods like cluster expansion, we can derive the model inputs using graph neural networks, but with this idealized XFCC representation. And since it's trivial to generate, we can screen millions of configurations. So you pretty much see no degradation in performance whether you use the relaxed DFT structure or this initial idealized XFCC representation. This is the test set predictions on the exact same configurations, and the error is pretty much negligible. So I see that I have only got about 10 minutes left, so I'm going to quickly jump through this and just say that basically, if you give these models a specific training distribution, they can actually do out of distribution predictions quite accurately. So when I screen a different composition than it was trained on, or different equimolar ratio, different ratios than what it was trained on, we can actually accurately predict those configurations. You can really push that to the extreme. We're applying this original model to really off equimolar compositions. And now qualitatively, each composition is well predicted. You can see that kind of the slope of all these lines is pretty close to 1 for the model predictions versus DFT, but they're off by kind of like a constant shift. So in order to do this kind of one-shot learning, you just need to add in a very small number of configurations across the endpoint compositions. And then that makes your ability to predict accurately at all these equimolar or off equimolar ratios pretty much more or less perfect. So we can then screen, across all of the composition space that we might want and predict, across all these different formation enthalpies. But of course, that's not what really matters for its synthesizability. What matters is the energy above the hole with respect to all the other possible compounds that exist in this elemental space. And so the fact that all these materials are, about 0.1 EV per atom above the hole suggests why experiments weren't able to make or only saw very faint signatures of this FCC alloy in their experiments. One solution could be to get rid of tin because that gets rid of the possibility of forming this strong magnesium tin intermetallic compound. But even still, you're going to be pretty far above the hole here. So unlikely that you're going to be able to make a material, a pure FCC alloy in this phase space. So finally, we redid this for now demonstrating it for hydrides. You can have the ideal representation for a hydride phase. Again, we can validate these models. They're extremely accurate based on these ideal representations for predicting hydrogen adsorption landscape in these palladium substituted systems. And again, these green points are materials that we've screened outside the original DFT data set, which we've revalidated to show that the model accurately captures lower and higher energy configurations than anything that's been trained on. Last thing I want to comment on the validation is that these models are very data efficient. You really only need on the order of 100 materials to get close to MeV, 1 MeV accuracy in these systems. So finally, for the price of just a few hundred DFT calculations, you can screen millions of configurations. What that allows you to do is go in and using first principles thermodynamics calculations, like either mean field approximations or anywhere from that all the way to full-on lattice model Monte Carlo, you can predict these PCT curves. And here I'm just showing that in the blue is when you use all the model screening predictions, and black and purple is when you try and use just the training data set, and you get orders of magnitude difference in those predictions of the plateau pressure. Every model used in this work was the exact same hyperparameters and model architecture. So this is just showing how transferable these models are. You don't have to think about it much. They're kind of just plug and play for doing these thermodynamic property predictions. Okay, and then so I want to conclude with saying that the key takeaways are that we can do data-driven materials discovery and diverse tasks, and the form of those efforts change significantly based on data availability and problem constraints. We've discovered new hydrogen storage and generation materials. or are currently working on that, the experimental validation. I think a big recent trend in these high entropy materials is going to necessitate the need for data-driven insights due to the combinatorial complexity of these materials. We can, predict just the primary property of interest to down select materials. And, a first principle simulation approach is going to also help give insights where ML can't, but oftentimes you can combine those two to get the best of both worlds. And then I've already covered these kind of summary figures, so I'll just skip that and open the floor to questions.
Thank you, Matt. Yeah, so we have some time for questions.
I think there are two questions in the chat. Hold on, would you like to?
Oh, yeah.
Address them first?
Yeah, so one of the two questions was, so Matt, you use oxygen defect formation energies as some descriptor, right? As some input. So, but this defect formation energy depends on where the oxygen defects are. So for example, in bulk and in surface, they have different formation energies. So which ones you input to your machine learning models, or does it matter?
Sure, yeah, great question. The machine learning model is, let me back up. The DFT data is constructed by doing these bulk defect calculations in supercells to make sure we don't have any, or minimize the finite size effects. So these are all bulk defect calculations. The underlying training data does not have any surface defect calculations in them. But in terms of what goes into the machine learning model, because you're just inputting a crystal structure, if we had DFT calculations that did represent, surface structures, there would be no change to the machine learning approach to actually do those predictions. You would just feed in, your slab model or whatever it is. So that's kind of what I meant when I mean, that's a good point. If I go back to this slide in terms of opportunities for next steps. So we want to start getting more structural diversity, and that could be 2D materials, but that could also, of course, be slab materials or defects that are where the local environment is not bulk but is terminated at some point. So yeah, thanks for the question.
Yeah. So yeah, and the second question, I think Max is here. Max, can you ask?
Oh, hi. Very nice talk. Yeah, so my question is in the chat. I was asking, are there any knowledge that material scientists would like to extract from your machine learning models, since they seem to predict and also generalize well? What will be the format of that knowledge? For example, does GM models reveal some kind of coarse governing equations? And also a separate question is, how do you measure epistemic uncertainty, or does the epistemic uncertainty really matter in your prediction or your optimization?
Yeah, great questions, thanks. So that's, I guess a bullet point I should have put here is, in general, interpretability of, these predictions, and how does that help us inform, can I as a human understand what is, gives me the ideal material that minimizes or maximizes defect formation enthalpy. So I would say that, we haven't made much progress on that front in terms of a human understanding representation of these. That's what these projects were kind of dedicated to, was right. So this is like a nice, simple linear expression that gives you the oxygen vacancy formation enthalpy in terms of physical properties you can actually think about. But you have this classic, trade-off between interpretability versus expressivity of your models. So, while this is limited to a certain, well, it's limited to oxygen and, perhaps certain crystal structures, ours is, doesn't have any limitations. All it needs is a crystal structure. That being said, there's like a really interesting recent paper. So I talked about SHAP analysis for the compositional models. Someone recently just did that for graph neural network models. Actually, I haven't even read it yet, but it looks like there's, that's a new push, I guess, in terms of the theory development in the CS world, is how do you, get interpretability, real interpretability from these graph neural networks. Some people say that they're interpretable because they look at this, final feature vector, and then they do a PCA or something, and then color code by the output property, and they see that the material, you get different domains that are of similar, similar property predictions in your PCA dimensions. But to me, that's not really interpretable. It doesn't tell me as a human, how do I choose a crystal structure to, from the, a priori get a target value, because it's, once you do PCA, you don't really know. I mean, you don't know what this X crystal means, and you don't know what the PCA of it means. So I think that's an active area of research that should be explored and, used to continue this project. Second question was on uncertainty. So for now, the only uncertainty we've applied is through through k-fold cross-validation. So we, because these models are fast, we can actually do even leave one out validation, or k-fold cross-validation. We train, however many models. We apply it to, the same prediction, all 10 or 100 models or whatever it is to the same material, and look at the standard deviation and say that's a heuristic way of measuring uncertainty. But that's certainly a biased way of doing it. So I think that there's going to be interesting future opportunities as well for doing a better job of uncertainty quantification. But the way we've done it is it helps us to identify really out of distribution materials very quickly. So like actually when you screen these materials projects, structures, there's things like metal peroxides, right, where the oxygen-oxygen bond distance is really close. Those are not anything like what's in the training data. What's really cool is the model actually gets those predictions qualitatively correct. It understands that the defect formation enthalpy is really low, but the uncertainty is quite large. So what we've used that heuristic uncertainty metric for is a way for experimentalists to filter down the list of materials and say, I'm not going to deal with anything that's got this large uncertainty, because it is at least, primarily an indicator that the material is significantly out of distribution with respect to the training set. So yeah, thanks for that question.
Mm. Oh, yeah, thank you. Regarding the first point, I'm actually not very interested in what the computer scientists will say about interpretability or explainability. I'm interested in what material scientists believe that the format of knowledge that they wish to extract from these models. Because when the material scientists criticize machine learning models by saying that, what do you learn? What's the science in these models, right? But at the same time, they also use these models without talking about the science. So I wonder, internally, do you have discussions on, well, what do we exactly learn from these models? I understand that there's maybe not much research going on, but is there a wish list, like a things that you wish to be able to extract from these models?
Well, so I mean, at its simplest, you can do things like post-analyze the predictions. So nothing really related to the machine learning component, but because you can get large-scale insights by screening everything, you can then kind of do, simple clustering, for example, and look at, so one thing that we've noticed is that most of the materials that fall within this critical range contain barium, right? So while that's not giving you structure level insights, that's for whatever reason saying that, most materials in this critical range for stitch contain barium, right? And that's, surprisingly consistent with other things where there's a lot of, experimentally looked at materials that, contain barium. So I would say that just the fact that you can do high throughput screening and you can look at, tens of thousands of predictions, you can do very basic, like, manual filtering of that data to get, chemical insights into what's going on, even if it's not directly related to the machine learning algorithm itself.
Mm-hmm.
But I do think that there needs to be another level of, of interpretability analysis, post-applied to model weights and graph neural networks that can actually somehow distill the information down into simple design rules, like we did with compositional models, where it's like, hey, well, actually, if you're designing a metal hydride, on average, if you substitute it with an element that, increases an UPA, on average, it's going to, increase the plateau pressure, which is, a very useful, simple way of just thinking about it and, taking a known material that works really well and slightly modifying its, its composition to potentially not affect anything related to its structure, but actually tune the pressure in the way that you want it to. So yeah, we need something like that for graph neural networks too.
Okay, yeah, I think there's another question from Mukesh Kumar.
So, and thank you for your nice presentation. And my question is, on the basis of these models, what you think 2D materials or thin films like couple of monolayers, such type of materials could be a potential candidate for hydrogen production or hydrogen storage applications?
Well, I mean, that's certainly an active area of research and literature. I can't say that these models help us inform, which materials would be useful for 2D materials or thin layers of 2D materials, just because I literally haven't applied the model to them yet. One thing that I've been meaning to do is, well, actually, we have an internal Sandia funded project related to this, so there will be some 2D material work on that. I'm planning on just applying these models to, thin films or something like that, and seeing, how well do they actually work in, these structure classes that are not represented in this training data. But I think that it's certainly a promising area, and understanding how well these models generalize to structures that aren't directly what's in the training database would be an interesting, next step.
Thank you.
Yeah.
Any other question? So Matt, I have a question. So in the liquid metal part, so what's properties are you looking for? Like just any combination of metals you form liquid, and then it will be a good candidate?
Yeah, so the main point was basically, okay, obviously it needs to remain liquid if we want to be able to do this, combined oxidation and this full redox cycle, right? If this material crashes out, it freezes out, it's not going to be useful. So I think what actually motivated this project is, you have the alga system, right? So people have actually looked at that for, for water splitting, this alga at certain molar fractions is liquidous at room temperature. So it's kind of attractive, right? You can you don't even need to apply any heat and it's liquid, but as soon as you expose it to steam, I mean, the formation of alumina is so strong that the material, essentially, what people have noticed is like, they can't really keep the system liquidous, and I've never seen any demonstration of it being reversible. So that was kind of what motivated this project, in terms of this holistic process view. And so the main things are, does the thing remain liquidous? And then how do you balance the strength of oxidation versus how difficult it is to electrochemically reduce afterwards. So I didn't show any of the electrochemical reduction experiments yet, because those are just being finished up now for this paper, and wouldn't be able to present on them well enough. But indeed, our collaborators at University of Tennessee have done, shown that you can take this tin zinc system that we've oxidized and fully reduce it back to its neat liquid metal state. So those are kind of the two main criteria, right? Is, does it melt well enough, and can you extract the information that you extract from these predominance diagrams, is that how does that allow us to qualitatively rank materials for experimentalists that say, we want to balance the strength of oxidizing the first metal, we don't want the second one to oxidize, and we want this balance to allow us to be able to electrochemically reduce the system to form the full redox cycle. So
okay,
that's a high level answer, I guess, to your question.
Thank you. Yeah, so Mukesh, you have another question? I saw you raise your hand. Mukesh. So any other questions? So if not, I think let's thank Dr. Witman again. Thank you so much, for joining us today.
Yep, thanks so much, Alang, and thank you for the invitation. And again, feel free to email me, anyone who's interested in asking more questions or discussing potential collaborations in the future.
Thank you.
Thank you. Bye.
Bye-bye.